In this video, we're going to start our implementation of our red-black tree. And where we're going to start off with is with the idea of rotation. So we saw when we were looking at fixing for inserts that we often had to do these rotation operations where we basically were moving each of the nodes in like a clockwise or counterclockwise notation through the actual tree itself. So we're going to implement these first because we're going to use them in a lot of the different operations that we implement in a red-black tree, so they're going to be pretty foundational. Before we start with that, we of course need a node, which I've implemented already for us here. This node looks really similar to the binary search tree, right? It has a value, a left and right pointer inside of it, right? But the main things that it has differently is a color and a parent. The color is how we're keeping track of the red-black property. You'll see that I'm using an integer to keep track of this rather than like text. In some cases, you may see text being used. I think text comparison is a bit too inefficient to be using for this case, so I prefer to use just constants that indicate red or black. We default our color here to black generally, since when we create a node that is a nil node, right, a node that has no values, the color of it needs to be black. So we default it to black to indicate that, and then we can change it if needed. We're also keeping track of the parent of the current node, and the reasoning for this is because there's a lot of different operations that require us to find the actual parent, right? You saw when we took a look at our insert keys, just almost every single time we had to go up to the uncle, which requires us to go to the grandparent and then go to the sibling of the parent. So in order to be able to do those kind of operations, we need to be able to track the parent easily, so we make it a property of the node itself. With that understood, let's take a look at the implementation of our red-black tree. So the start of this is basically, I'm just going to create a class to store my red-black tree, right? And inside of this, we'll do our initialization. And in our initialization, I'm going to create this nil node, which is just a node with a value of 0. Basically, what ends up happening here is the node will have a value of 0. Everything else will be none except for the color, which is black. This is what we indicate as the nodes that are the null. They're basically the equivalent of the none nodes in our binary search tree. It's just a reminder, the reason for this is because all of the leaf nodes have to be black. So rather than letting them be none with no color, we want them to be either red or black. So we keep track of that using these nil nodes. Similarly, these nil nodes will have pointers to parents eventually, which makes it much easier for us to iterate the tree from the nil nodes if we end up at them to be able to find actual parents for the nodes that we're working with. So those are the two main reasons that we might want to use a nil node generally in this tree. So what we do next is we create the root. I'm going to set it equal to the nil node because it currently is nothing at this point. And then I'm going to create my rotation. So there's two rotations that we have. We have a right rotate and a left rotate. I'll actually start with the right rotate here. And the idea is that it starts at a node. And what it does is it starts by getting the left child of the node that we're at. And then it sets the left equal to the right of the left child. So when you're envisioning this kind of rotation, right, just imagine that like the left and right are essentially swapping their places with each other, right? So you can sort of visualize that idea. And what we're going to say is we're going to say if that swap that we did, right, if that doesn't end with a self.nil, then we're going to say the left child dot right dot parent is equal to the current node that we have. So we're starting on the actual movement of the nodes themselves. Then outside of the if statement here, we're going to say that the left child's parent is going to be equal to the node parent, right? And then basically we just do a few more checks to complete our rotation. So we're going to check if the node parent is equal to nil. If it is equal to nil, then that means we must be at the root. So the root becomes the left child, right? The only thing that doesn't have a parent is the root, right? It's sort of the start of everything. There's nothing above it. So if we see that the parent is nil, then we must be at the root. Otherwise, if we're not at the root, then we're going to check if the node that we have is on the right-hand side of the parent. And if it is, then what we're going to do is we're going to do node.parent.right equals left child. And then on the other case, we're just going to do node.parent.left equals left child. And then finally, we're just going to set the left child's right equal to the node that we took in. And then we set the node.parent equal to the left child. So this is how we do the full rotation, right? And what you're visualizing here is really more of like a clockwise, or in this case, counterclockwise rotation through the actual tree itself, right? So we're actually moving the nodes up and around in order to rotate through the tree itself. Now, something that's really cool about red-black tree properties is the symmetry that exists in them. And we're going to see a lot of different kinds of symmetry. And one of the first ones that we'll see is that the left and right rotate are very, very similar to each other, right? So the idea here is basically that this ends up becoming the right child, and it's equal to node.right. And then what we do is we say node.right equals this dot left, right? So basically all of the lefts change to rights and all of the rights change to lefts, right? That's really all that ends up happening here. So we basically just make these simple adjustments and we end up with our next rotation. And you're going to see this process very, very commonly, that we just are going to be changing left to right and right to left. And I'm going to continue to point it out everywhere that I see it because it makes a lot of sense to keep track of this information, because otherwise you're going to be memorizing a whole lot of code that you don't need to actually be memorizing, right? And that's going to be really not beneficial for you at all, right? Because it's kind of like wasted time to memorize when you could just remember one and then flip the left and right each time. So see here, generally all I'm really doing here is I'm just flipping left and right wherever I see them. And that's really all there is to it. That's how we end up with our actual code for the rotation. So there you have it, right? So you can see that basically these two rotations are symmetrical with each other. One of them starts with the left-hand side of the node. The other one starts with the right-hand side of the node. And then from there, we just move through the tree rotating based on where we started. And that's how we end up with our left and right rotations. So both of these rotations are going to be core for the actual insertion fixes that we're going to talk about in the next video. So basically in the next video, we're going to actually do our insertion and we're going to utilize these left and right rotations in order to move our nodes through the tree. So we'll take a look at the details of that in the next video. Thanks so much for watching. I'll see you in the next one.